So here we have limits at infinity. So this is really the first time we've ever looked at this. This is the case where you're actually, the value of x is going to plus or minus infinity. And now that if x is going to negative infinity or positive infinity and it approaches a number, L, then that has to be a horizontal asymptote. So that's your definition of a horizontal asymptote. And it makes sense if you think about it. So I have this function here, and I don't care what the graph looks like, but say your x is going all the way to infinity. If your graph approaches a single number, say 1-ish, then by definition, that's a horizontal asymptote. And say when you approach negative infinity, the graph also approaches a number, say -2 maybe. That also by definition then is a horizontal asymptote. So basically a horizontal asymptote is where a graph evens out. Now, if you remember horizontal asymptotes, it was very rare that you saw 2. Usually we saw 1, but that happens for rational functions, and that's what we're going to be talking about. So here's 3 functions. And these 3 functions look pretty similar, but pay close attention to the degrees. If I was to ask you, okay, let's figure out what this limit is. I said x is going to infinity. Well, you can do it numerically, and you can just type in infinity to all the x's, which you can't really do, but I'm using this number. So I know I'm getting close to infinity. And when I plug that number into this function, notice what the answer comes out to be on the calculator. 1.33 times 10 to the negative 7, which would mean 0.000000001. So we're going to say that is going to approach 0. And if I use more zeros on this, I have here a trillion maybe. If I use more zeros, this number will get closer and closer to 0. So I want you to notice here that the degree of the bottom was 3 and the degree of the top was 2. So when the degree of the bottom is bigger, when you plug in like a huge number, the bottom's always going to be way, way, way bigger than the top. And when you get a small number over a large number, you will always get 0. Let's look at this one. The next one, we're going to negative infinity here. But now the degrees are both 2. So when I type that into my calculator, now I'm using negative trillion here. My calculator gives me the answer of 1.333. So all that's saying is, as you go to negative infinity, this graph does have a horizontal asymptote. It does approach number 1.333. So that's what happens. You may remember this from last year or Algebra 2. If the degrees are the same, this will approach a horizontal asymptote. It would be these leading coefficients, 4/3. So this number is going to get closer and closer to 4/3 as these numbers get larger. And finally, the last one. Notice on the last one, the degree of the top is 4. That's bigger than the bottom. So when you do that, again, I'm going to positive infinity, so I'm going to plug in a very big number. It's right here. You'll see that when I do that, this number, the result, is getting bigger and bigger and bigger and bigger. In other words, it doesn't approach a number. Therefore, if you're looking on the horizontal asymptote side of things, this one does not have a horizontal asymptote. So when you're looking at a rational function, and a rational function is a polynomial over a polynomial, so all these are rational. I'll show you a non-rational function next. But when you're looking at a rational function, here's all the rules you learned in Algebra 2 and trig. If the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote of y equals 0. Or a limit, an infinite limit that goes to 0. Because infinite limits and horizontal asymptotes are synonymous. If the degree of the numerator is the same as the degree of the denominator, then your infinite limit would be equal to the ratio of the leading coefficients. Or, in other words, you have a horizontal asymptote at the ratio of the leading coefficients. And lastly, if the degree of the bottom is bigger, if the degree of the top is bigger than the bottom, the last one, then it doesn't approach anything. Your infinite limit will not approach a number, and thus you will not have a horizontal asymptote. So, all of these guidelines should be familiar to you. That's what we use to find horizontal asymptotes. But since horizontal asymptotes and infinite limits are the same thing, you can use those rules to find infinite limits of a rational function. So I have more to show you, but I just want to do one quick example, or maybe two examples. So if I said, what's the limit as x goes to negative infinity of the function 5x to the fourth minus 2x plus 1 over 8x to the fourth minus 12. Well, you know this is really going to find a horizontal asymptote. Since the degree of the top and the bottom are bigger, that's the result of the limit. Now, you could ask the question this way. Determine the asymptote of the function f of x equals x minus 7 over x squared plus x. What that? Well, now we're not actually doing limits, but you do have to think in terms of limits or asymptotes. And you have to remember this could have vertical and horizontal asymptotes. So first we'll take care of the verticals. The vertical asymptotes would happen where the bottom is 0 and the top is not. So the first thing I'm going to do is factor. You can see that the bottom equals 0 when x equals 0 for the first factor, and when x equals negative 1 for the second factor. So these are the vertical asymptotes. Don't just write 0 and negative 1. Vertical asymptotes are equations of vertical lines, so they all have to have x equals. Then it has horizontal asymptotes. Horizontal asymptotes look to the original function. Notice that the degree of the bottom is bigger than the degree of the top. So by definition, that would have a horizontal asymptote at y equals 0. So that's how you would answer that question. Now, all rational functions have only one horizontal asymptote max. It can't have more than one. You're going to see that's not the case for rational or radical functions, and that's what we're going to be looking at next. So that will be the next video.